We're doing electromagnetic theory, and in the last lecture we saw electromagnetic plane wave propagating through space, free space, and we looked at the differential equation and the solution thereof. And in this particular session, we're going to look at the energy issues here, how the energy flows with the electromagnetic wave. For instance, light is coming from the sun to the earth, and how the Poynting vector behaves and how the average energy density fares out. We're going to look at that. So when electromagnetic waves, they travel in free space, we have both electrostatic energy density as well as the magnetostatic energy density associated with that wave. And let me just denote the electrostatic energy density as UE and magnetostatic energy density as UM. Then we've already derived this in our previous sessions and previous classes. The electrostatic energy density is given by half epsilon 0 E square, where E is the electric field. And the magnetostatic energy density is given by half mu naught H square, where H is the magnetostatic magnetic field vector. Now, if you take the ratio of these two, then you can see here there's a common factor of half which gets cancelled out, and the ratio comes out to be epsilon 0 over mu 0, and then we have E square over H square. Now, there's one particular section where we take the ratio of E square and H square, and that comes out to be the speed of light, something of that sort. So let's just take a look at that. So we saw the solution of this plane wave, the plane electromagnetic wave propagating in free space. The solution was of the form that E equals E naught. So you have this electrostatic field, this particular field, as E, which is a function of r and t, where r is the position vector and t is the time. Okay, this came out of the form E naught e to the power I, and then you have the wave vector k dot vector r minus omega t. So this was a standard solution to our wave equation, and we have a similar solution for h. So if we take the ratio here, then we just get the average value of these two, which came out as z naught, and z naught came out as under root of mu 0 upon epsilon 0. And we also calculated this value as these 376.7 ohm. This is called the impedance of free space, and we did that. So I can replace this particular value by z naught, or the impedance, the square of the impedance, because it's a square here for both. And this in fact can be replaced with this, and you can just square this value. So if you square it, the root goes. So this comes out to be epsilon 0 upon mu 0, and this particular portion would be mu 0 upon epsilon 0 if you factor out the root as well as the square, and these terms get cancelled out. And there's a very interesting thing that comes out here, a really interesting feature, that the ratio of UE and UM is 1, and what essentially that means is UE is equal to UM. So if you look at the physical aspect of this, this actually means that the energy is equally distributed between the electric field and the magnetic field. So the electrostatic magnetic energy density is actually equal to the magnetostatic energy density. In fact, they complement each other perfectly well, and the ratio comes out to be 1. So that's how the average energy happens in the electromagnetic wave just traveling in free space. So now we have to look at the Poynting vector too, because that tells us the direction of flow. So here you go. Those are the steps which I worked out earlier. They are displayed here on your screen right now, that UE is equal to UM. And here's a conclusion which says that thus, when an EM wave travels in free space or vacuum, its electrostatic energy density is equal to its magnetostatic energy density. So that's one part, which is the energy density and how the energy is distributed between the magnetic field and the electric field in case of plane electromagnetic wave propagating through free space. The next aspect, as I mentioned earlier, we have to look at the Poynting vector, and we all know the definition of Poynting vector. It's actually the cross product of E and H. E cross H. This is your Poynting vector. So we've got to calculate this, and let me remind you, in our previous lecture we have already calculated this. So we had something called K cross E. We had calculated this quantity and IK cross E, and it was basically I think it was mu naught omega H that we calculate this as. So we can use this particular concept here and see how the Poynting vector turns out. Okay, so let's see how that proceeds. So here we have, so K cross E, we have already worked out it's mu naught omega H, and E cross H would be E cross, and then I'm just taking out the value of H from here. For this, I have to divide both sides by mu naught omega. So I can factor out mu naught omega on this side. And you can see that, cancel this out, and you got the value of H as K cross E over mu naught omega. And I plug it here in this. And you see that S equals E cross K cross E over mu naught omega. Now this K vector, it's a wave propagation vector, and we know that the electric field vector and the magnetic field vector, they are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. So this K basically is in a direction normal to this, and if we denote this, the direction of K as n cap, n hat, then you can write the K vector is the magnitude of K times n hat. All right, K vector can be written as that. So I'm writing it like that. So I've taken the magnitude of the K vector out here, and I split this vector into K magnitude times n hat, and I've taken the n hat in to have that effective cross product. So this basically works out as K, this magnitude of K vector. I've written it as in caps here, but this basically generally is written in small letters. And here you have mu naught omega. All right, and then inside you have a vector triple product. So I hope you remember the formula for this, A cross B cross C. All right, and if you don't remember, there's a simple way of memorizing it, and that's back cap. Back cap means B A dot C minus C A dot B. Back cap. So if you remember this, you can get this triple product where A is this E vector, B is this N vector, and C is this E vector. And if you apply that here, so we have A dot C, which is E dot E, times B, which is N cap or N hat, and then we have E dot N times E vector. And well, here the dot product of perpendicular vectors is 0 because cos is 90 degree, and angle is 90 degree, and they're in the same direction. The angle between the electric field vector and the propagation is 90 degree, and cos 90 degree is 0. So this term vanishes here, this term. So we're left with this E dot E, and this should be actually E square magnitude, because the dot product of two vectors in the same direction, same vectors in fact. So E square n cap over mu naught C, and this is basically Z naught. 1 over mu naught C is 1 over Z naught. We worked that out earlier. You can see the working out here too. I worked it out here too. So it's 1 over Z naught. So this is the Poynting vector. Now this is the instantaneous Poynting vector. But we are more interested because the electric and magnetic fields, they vary at such a fast pace, such a fast frequency that I mean, point vector at any point of time, the instantaneous vector doesn't make any sense. So the more acceptable quantity is the average of the Poynting vector. So average is here, which is average of this term square times n cap, and E square, if you just break it down to E naught exponential I k dot r minus omega t square, we take the average value of the real part of this, okay, and that comes out to be this needs some mathematical working out. This must have been done, the calculation of average values, in your vector calculus class earlier in the math section. So this averages out to be E square over 2, the average value of E square, this expression, the average value of this expression, and of course we have to take the real part of this. It comes out to be E square over 2. So the whole thing becomes E square, E naught square over 2 and n cap over z naught. And we also know that we can just take the root, square root of this E naught square over 2. You can see here. So if you take the square root, then this becomes E RMS. So if you have E naught over under root 2, the whole square, so this becomes E RMS square, root means square value, RMS square n cap, right, over z naught. That's equal to average value of Poynting vector. So there it is. And of course, we know that total energy density is UE plus UM, and they're equal. So you can have it as twice of UE, and that would be twice of half epsilon 0 square. So half gets factored out with 2 here, 2. So this is equal to actually 2 into half. That's the electrostatic energy density, epsilon 0 E square, and you have this 2 canceling out here, and you just have epsilon 0 E square here left. So that's your energy. And if you take the average value of U, again, you'll have to take the epsilon 0 and average value of E square, which is E naught e to the power I k dot r minus omega t, and take the real part of that and take the average of that. That comes out to be E naught square over 2. We just saw that earlier. So this becomes half epsilon 0 E square, E naught square. So we can see that if you compare all these equations, this Poynting vector S, okay, which is this quantity, and this U, you can see there's a relation between them. The Poynting vector, average value of the Poynting vector is equal to the speed of light times the average energy density times the n cap vector. So the n cap is the direction of propagation, which is perpendicular to both E and H. This expression shows that the wave is traveling in a direction perpendicular to both E and H, as well as the energy is also flowing in that direction. So that's how we receive the energy from the sun, and it is approaching us. This whole energy density is approaching us with the speed of light, that is 3 into 10 to the power 8 meter per second. And we all know that light takes 8 minutes, about 8 minutes to reach Earth from the sun. And that's the math behind it. No experiments here, just plain simple laws of electricity and magnetism, and that's how we have been able to treat the electromagnetic wave propagation in free space. So that's the end of it, and I'm going to see you in the next one, where we'll be looking at a dielectric medium and how the wave propagates in a dielectric medium. Thank you.